Hey everyone, want to welcome you to the next Math for the Impatient with our CTO and co-founder, Stan Kladko. Today, we're going to talk about performance, which is always an important issue when it comes to blockchains, because obviously the faster they run, the smoother they run, the more people can have an amazing experience. So let's talk about, I think first, Stan, improving the performance of scale chains. So why is performance important for Scale, and what computational tasks do scale chains typically perform?
Yeah, that's a great question, Marcus. I will start by saying that when we started Scale, we always understood that performance is critical, in particular to Scale, to us. And why? The answer is because, as we discussed already many times, our transactions are free. Our entire idea is that we provide free transactions, we provide many chains, and we want to serve millions of users as compared to others serving thousands of users. It's because we actually want transactions to be free, our computations need to be super effective. That's why from the start, when we built Scale, we actually targeted performance so much. And one of the early decisions was to use C++ as the programming language, which originally provided to us lots of performance advantages. If you look at Ethereum mainnet, it's built on something which is called Go. It's a programming language which is really fast to program, but it's really slow. So the typical mainnet node of a mainnet network of Ethereum is slow, but it's not so important because there are not so many transactions on Ethereum, and also because the transaction fees are so high. You can afford to run slow programming language. And the great thing about programming languages which are slow, they're easy to program and fast. So Ethereum was built, in months, right? In our case, the idea is a little bit different. We want to be as much performant as possible because we want transactions to be free. And initially, many things have been done to improve performance. One of those things was that we used C++, which is a programming language which is probably like 10 times faster than as compared to Go, right? Another thing was for us to use a super effective consensus, a super effective cryptographic algorithms like BLS. So always when we were building our network, we were thinking about performance, and sometimes it actually meant that we would have to code more, and the product would actually take longer time to build. But now we have the product, and I must say that our product is definitely the most performant product far on the market. There's nothing even that compares to it. And because it's performant, we are able to run not a single chain on a server, but 8 chains. Our chains run on medium size and medium price AWS servers, and we're able to run 8 chains per server, which actually decreases the cost 8 times. So when you have a scale chain, it's not actually executed by a particular AWS virtual machine. It's executed by 1/8 of this machine. So Scale version 2.0 is pretty performant. But now we have this next step. We need to make it even more performant. And the reason comes from the fact that we expect our user base to grow fast. And we want to have millions of users. And as you imagine, if users grow, they start loading the chain. They start sending requests to the chain. And yes, we can actually start more chains, but it would be nice also to be able to handle more users by a particular chain. And that's why in Scale version 2.1, we are putting so much emphasis on the performance. And then, there are several things. If you talk about performance, it's not actually a monolithic thing. There are 3 things in performance which are important. Scale chains do 3 things. One thing is something which is called consensus, meaning that they actually built the blockchain. You know, people send transactions to the blockchain, and these transactions get ordered and glued, and ultimately you have the chain, which is the same on all nodes. So this is something which is called consensus, and part of our computational performance goes into the consensus. That's number one. Number two is actual transaction submission. Before the transactions are actually included to the chain, they have to be accepted from the user. They have to be broadcast to all nodes in the chain. And this part is also pretty computationally intense and also network intense. And the third thing is something which we call read requests. If you want to know how much money you have on a particular chain, you issue a read request. If you want to call a particular smart contract and you want to find out its state, you want to find out how is it doing, you issue the read request. So the third thing which actually loads up the chain are the read requests. And imagine if you have millions of users, all of them issuing read requests to the chain, this can also take CPU time and network performance, and also things like blockchain browsers, right? We have like blockchain explorers which run on Scale, and these guys constantly ask the chain about all of the blocks and transactions. And when you go to a blockchain explorer and see all of the things nicely in a web browser, guess what? You know, the blockchain explorer actually constantly loads the chain and issues requests to find out how the chain is doing. So there are these three types of requests: consensus, which is the core thing. You have the transaction submission requests, and then you have the read requests. These three things actually computationally load the chain. And if we want the chain to perform better, we need to actually, for each of those things, figure out how to run it cheaply, how to spend less computational resources, how to run it fastly, all these kind of things. And this is something that we are planning for release 2.1. Release 2.1 will be heavily about performance, because we understand that now we have so many chains to create. Actually, after like several weeks after release 2.0, we'll have more chains than all of our competitors combined. These chains will all run, people will use them, they will issue all kinds of requests to them, and we understand that we need to improve performance in parallel to user growth so that the chains don't actually get stuck or don't get slow. So this performance thing is a super important thing for us now.
Very cool. So just to clarify a couple of interesting things, I think, for folks. One is we're decentralized, which means we don't run a single node ourselves, unlike a bunch of the other folks who are out there. And that's really important because it's a core concept to Scale. So when we talk about those nodes being run, those are nodes that are being run by any of our 46 different validator orgs. And then I think another thing that you pointed out, which we don't really talk about very much and you don't hear very much, is it's really fascinating that Scale is built using C++. Which is a much more performant, much more scalable, also really well understood programming language. And that's, I think, a really a key differentiator. So you talked a little bit about performance on Scale 2.1. So there is this thing called Scale Power Mode. So tell me a little bit more about that.
So Scale Power Mode is an immediate way for us to drastically improve performance. We need something next month, because as people start using our apps, we want those apps, those games, to grow virally. We want actually to do something that no one actually was able to do in the past, to grow to millions of users. And we understand that this will actually create lots of problems in terms of performance. So we need to basically build this performance plane. We have the plane, but we need to improve the plane as it's actually flying. Imagine that you have a plane and you need to install a new engine. Basically, that's what we'll need to do. If we don't do that, things will get stuck, will get slow. So we do have pretty high pressure in engineering to deliver. So we have this concept of a power mode, which we think can actually improve performance drastically in release 2.1 without actually compromising decentralization. And then to understand how the power mode works, let's again talk about these three tasks. We have the blockchain does consensus. It orders transactions in a chain. It also, this is really the thing which needs to be decentralized, because there's the entire purpose of the blockchain to create the blockchain in a decentralized way and also distribute it in decentralized way to all nodes, right? This is the core. But the two other things are not really the core. There is a thing which is called transaction broadcast. Before the transaction is included into blockchain, it needs to be broadcast to all of the nodes. And currently, the nodes do it themselves. So you submit the transaction to the first node, it will broadcast it to all other nodes. And the last thing is read requests. And again, currently nodes take all of those read requests. But now, as you imagine from our previous sessions, we have these full sync nodes. Full sync nodes are replicas, which are not security relevant replicas. Those are just replicas that community members can run to have their own copy, basically, of the chain, to have their own dynamic, constantly updating copy of the chain. That's something that we call replica nodes or full sync nodes. And we're about to release them, I think, within the next couple of weeks. So these full replica nodes, they actually have the entire copy of the chain, but they don't really play any security role. They just copy the chain. Now, what we are planning to do is also add to these replica nodes ability to respond to read requests and ability to broadcast transactions. So out of those three computationally intense tasks that I mentioned, that currently in release 2.0 are all performed by the core nodes of the chain, out of those three, we're taking two out and just leaving the consensus part on the core nodes, and the other tasks, read requests and transaction broadcasts, can be performed by the replica nodes, by the full sync nodes. So then the community, if you say we have a very successful DApp, and the community sees for this DApp that, so many users using this game or this DApp, right? The community of this game or this DApp can actually run independently additional servers to become those full sync nodes or replica nodes. And these full sync nodes will accept transactions from users and broadcast them to the core. They will also respond to the read requests. And we won't even manage them. The decentralization or whatever management of those replica nodes, full sync nodes, will be actually managed by the community, by the game, by the DApp, by the DeFi app that runs this particular chain. So the great thing about this is that, we're also giving them the power. These nodes are not going to be nodes belonging to the core SKALE chain. So the idea is that if you are out of three tasks, if the core nodes only do consensus, it also protects the core nodes from denial of service attacks, because the users, the anonymous people from internet, they won't directly interact with the core nodes. They will actually interact with replicas when they send transactions, when they read results. And if a bad guy somewhere across the planet wants to do a denial of service on a SKALE chain, guess what? This person won't be able to do it because SKALE chain won't accept these things, these requests. The SKALE chain will require this person to go to the replica nodes, to the full sync nodes, and if there's a denial of service attack, the community that runs this particular DApp can always increase the number of the nodes to protect against denial of service. So that's pretty much the idea about the power mode. It's very simple. You have the core chain. You are also letting anyone, and for the most part, the community, to run these security non-relevant nodes that only do read requests and transaction broadcast. And then if you need more performance, you just add those nodes, and the core blockchain does the only single task. It actually does orders the transactions into the chain, and also provides the master. the master replica. So it's actually very much, if you think about this in terms of like customer support, like in customer support, you have first line and second line. Like if you have an IT product and someone asks a question, it first goes to the first line where support person responds. And then if the question becomes really hard, then it goes to the second line. Very much the same idea, having this full sync nodes or replica nodes as the first line, and then chain in the core being protected essentially. Think about these guys as guards, that guard the actual core chain. So the core chain has the single task of ordering transactions and being the master, the source of truth, the source of secure truth. So that's something that we are planning for release 2.1. And I suspect that there will be lots of pressure and people will say, where is the thing? Because at the moment where we are doing this, the DApps are launching. For sure, as users grow, there will be a significant stress put on our performance. But we do have this kind of solution, which is fast enough so we can release it in 2.1. And this solution can alleviate the performance problems significantly.
Very cool. Okay, so we've got power mode coming in a future version. So what are some of the other improvements for performance that are scheduled for version 3, which is a little bit further out?
Version 3 is totally different, right? It's the next big thing. And version 2.1, the idea is that we are so pushed to deliver it yesterday. We have so many customers, chains. It's just crazy. We need to do something fast. Version 3 means that we will have more time to think. And so version 3 will actually include performance improvements, which take long time to discuss, architect, not long time, but medium time, because it will still be released in 2022. But still, there will be a process of architectural discussion, things. So something that can drastically improve performance. One thing which we cannot compromise is compliance and compatibility to and with Ethereum mainnet. So we need to improve performance, but we need to stay compatible, because that's the entire point. If we wanted to be incompatible, we could improve performance easily, but we need to be compatible. So the question becomes, how do you make things run fast if initially things were kind of designed to run slowly? Because, if you look at Ethereum mainnet, it hasn't really been improved much for the last, 8 years. There was not so much of a change in terms of performance, at least. Smart contracts, the Solidity programming language, and frankly, there was not also so much of a need, because Ethereum network has so much money coming from transaction fees. It's enough to actually, run slow software, basically, right? So Ethereum software from the beginning was based on the idea of running actually slowly and being programmed in Go. And now we need to make it run faster by doing incremental changes and not breaking performance. And there are two things that need to be done in order for the entire thing to run faster and more efficiently. One is network. Ethereum transactions are extremely large. They're very large. If you're just sending like one ETH to another person, it will actually require 200 bytes. Imagine if you're writing a check to someone, and each time you write a check, you need to write 200 characters. Even humans don't do this, right? 200 characters, think about this. If it's like 40 characters per line, it's like almost a page of handwritten text, right? Usually I would say that the typical person that writes a check, writes 20 bytes. You write the number, you write to whom is the check to, and something other things, right? 20 bytes. But it's funny, humans write 20 bytes and computers write 200 bytes. And it's just very inefficient. Many of those things, believe it or not, are zeros. The way Ethereum functions, you just write many zeros. You actually use these huge addresses that, huge. If you see now like Ethereum address, it is huge, right? And also you end up signing this using something which is called an ECDSA signature, which is also a very ineffective signature by today's means. You have about 60 bytes in the signature, and now you can do a signature with probably like 10 bytes using BLS. So the idea, you can keep things being Ethereum compatible, but you can replace long addresses with short things. You can just name persons by a number or accounts by a number. It can be account number 1, account number 2. So instead of sending to an address, you can say, I send to account number 5, right? And then you shrink the information so much. You can use BLS signature, which is drastically shorter. And in many cases, there are lots of zeros in transactions. Just compress those zeros or eliminate them. So we believe that we can drastically shrink transaction size from probably like 200 bytes to something like 20 bytes. And we need to still be Ethereum compatible, so it will require some engineering because it needs to work with MetaMask and other things. So, but if we shrink signatures, if we shrink the transaction size, a typical transaction size, 10 times, we can actually send 10 times more transactions through the network, right? That's why it's drastically important, because lots of the performance comes from how fast things go on the network, especially because, when people run like Ethereum or whatever nodes on AWS, when AWS starts expecting that some nodes run Ethereum, it actually starts throttling the network. In general, providers like cloud providers, then they don't really like crypto, because crypto does lots of computational power and also lots of networking. So we see lots of networking throttling happening on AWS or on other providers, where your network becomes, the bandwidth becomes really limited, and it's super important. If we can drastically improve the size of the transaction and make our network load less, this can drastically improve performance. So many ideas for release 3.0 will go into drastically improving network footprint and shrinking transactions. That's number one. And number two is, how do we make transactions to execute faster? Having that, as I already mentioned, transactions are currently executed by something which is called EVM, Ethereum Virtual Machine, which is first written in Go, which is really slow programming language. It's probably like 10 times slower than C++, right? And second thing, the Ethereum Virtual Machine itself, believe it or not, it's another slow programming language running on top of Go. So it's not just Go, it is Solidity running on something which is called the Ethereum Virtual Machine, which is written in Go. So because of the slow Solidity language running on a slow virtual machine, which is written on slow programming language Go, you have incredible inefficiencies, which explain why things run so slowly, right? If you write, like, if I just sit down now, write a program in C++, which essentially in the database sends one number or one token from one database account to another, I can do this probably, I can do probably like 100,000 transactions per second easily, right? But when it's all done and Go in Solidity, I go from 100,000 to 100. I literally have 1,000. I drop 1,000, basically factor, right? So, but we need to keep actually compatibility. We cannot just throw out a Ethereum virtual machine and write something new, which is written in C++. So the idea is that another big idea for us is to write parts, to rewrite pieces of Ethereum virtual machine in C++. And the question is, which pieces, right? And the answer is you need to find 1% of code which is executed 99%, right? Like you have lots of code in Solidity, but you find the hotspots. You write where like one token is transferred to, like ERC20 token is transferred to another ERC20 token, or NFT token is transferred to another NFT token, right, or another user, right? And these parts will actually be executed 99% of time, while creation of NFT token will be executed 1%, right? You create the token once, you move it 1,000 times. So basically the idea is that to get improvements fast, you identify pieces of the code, not the entire code, but pieces of the code which are called hotspots, pieces which are executed frequently. And if you identify those pieces, you actually rewrite them in C++, and then you can get this drastic improvement. And then obviously, what are the pieces? Obviously, the two pieces which are the mostly used are transfers of NFTs and transfers of ERC20 tokens. So the idea for release 3.0 is to be able to find out these hotspots and rewrite them in C++. And it's going to be an ongoing project because we do some hotspots in 3.0, then there will be more in 4.0. So we actually need to have this evolution where the performance of Scale constantly improves. And as years pass, hopefully we'll get more and more improvements. The last thing, there's another big thing, is that people constantly tell us that if you want to program something in Solidity, it is not only slow, but it's extremely difficult. People starting to do more mathematical calculations. They start to actually run more complex games. And in games, for instance, when you start like moving your characters like in a game, you want the character to move in a nice way, not to be a stupid guy, but to be a smart guy, right? So you need to have this AI for the game. So basically, you need more mathematics. And a big thing is that we need to drastically solve the problem how you do more mathematics in Solidity. Because for game, definitely what Solidity currently has is extremely hard and is insufficient. So the direction number 3 is to be able to execute some pieces of Python inside Solidity. And why Python? Because Python currently is the most used language in mathematics, the most used language in AI. It's such an easy language to learn. And so we are thinking about ability for people keep Solidity, but if they want, they will be able to intermingle this Solidity code with Python code. And then if you have Python, you can write many things on your own, but no one nowadays writes code. People just take code from GitHub, right? And so with Python, you have this immense ability. If you want to do something nice, you just go to GitHub, find things, and you put them in your code. So if we can add Solidity, Python to Solidity, we're opening this Pandora box for people to innovate and use much more mathematics and kind of go to the next generation of blockchain where it's actually really user-friendly for programming. And also Python, I forgot one additional thing. Python is not only the language for mathematics, it's the language for web now, for web development. So if you want to move a website to blockchain, you need Python. Like people come to us and they say, okay, we want to move our web to site to blockchain. We want to do like a social network. We want to do this. We want to do e-commerce. We want to do that. And they have lots of code in Python. And it becomes, it's extremely hard, as you imagine, to actually take this code in Python, move it to Solidity. Solidity programmers are really hard to find and stuff. So if we are able to run Python inside of EVM, then lots of current websites will be able to not only to move to Web3, but move to Web3 without actually hiring new people and in a reasonable time frame. So the last direction for performance is Python. So there's a huge field, and we think for the most part, we have the product now. So performance is the thing that we will need to concentrate on, not only this year, but for years to come. In addition to that, definitely usability, definitely making the product simple to use for users.
Very cool. All right, awesome. Well, a lot going on there, a lot to unpack. Thanks for doing this latest one. If you go down, you'll see our Twitter, you'll see our Telegram. Please join all the channels. Thanks, Stan.
Bye, guys. Talk to you next time.
See ya.